Okay, the purpose of this video is to provide an introduction to Thevenin's theorem. This video probably won't have any examples in it and will probably be pretty short, but subsequent videos will have plenty of examples to show you how to actually compute a Thevenin equivalent circuit. So the idea behind Thevenin's theorem is the following. Suppose I have a whole bunch of circuitry, and this whole bunch of circuitry includes one or more independent sources. That's what I've indicated here. And it's got other stuff. And the other stuff could be resistors or dependent sources. And Thevenin's theorem says that all of this stuff, which is the other stuff plus the independent sources, is equivalent to a single voltage source in series with what we call the Thevenin resistance. So a single voltage source in series with a resistor. And it's equivalent in the sense that it has the same voltage current characteristics of this whole blob of stuff. So this is really a useful thing to be able to do. Because, for example, I might have an amplifier. So this blob would represent an amplifier with lots and lots and lots of components inside of it. But as long as it's made out of linear components, which includes independent sources, dependent sources, and resistors, at least at this point. Later we'll introduce other linear components. Then I can replace the whole amplifier with just a single source and a single Thevenin resistance. This makes life easy when I need to interface the output of this amplifier to other things. I also might use this to model a sensor or a transducer that has a whole bunch of internal components, perhaps, but I can model it as a single source plus a resistor. Now, if I have no independent sources, so that would be this case, and I have just stuff, where again stuff is resistors and dependent sources, then it turns out the equivalent circuit is just a resistor, which is the Thevenin resistance. Again, this is extremely useful because I might have something that has all kinds of stuff. Again, for example, it might be an amplifier, or it might be speakers or something like that. And I can take all of this stuff and combine it into a single resistance. When I'm using this to do analysis, typically in the case here, the yellow case where we have independent sources, this R Thevenin is oftentimes talked about as the output resistance of this whole blob of stuff. In the case where I have no independent sources, quite often I'm connecting the stuff to other circuits that have independent sources, and so this R Thevenin quite often can be considered to be an input resistance. So it's, again, a very nice and simple way of modeling complex stuff. Now, quite often when you see this the first time in a circuits course, it's presented as just yet another way to solve circuits, and it turns out that if you're trying to just solve circuits with this, you're better off using nodal analysis, because it takes a little bit of time to get your head around it. It's not always obvious what you want to do. But when you think about it as a way to take a whole bunch of stuff and represent it by a single source and a single resistor, then hopefully it becomes clear that it is worth the trouble to figure out how to do it and how to use it. So when I say that these two are equivalent, that is, this whole bunch of stuff and this single circuit with a source and a resistance, what I mean is that the voltage-current relationship of the two are the same. If I draw the voltage-current